Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to be going over a problem in which we need to decide if this reaction is first or second order with respect to the data that we're given and in respect with this substance here, ClCO2 or CCl3. So let's get into this. So in this problem, we're asked, or we're given, the following gas phase reaction was studied at 290 degrees Celsius by observing the change in pressure as a function of time in a constant volume vessel. And here's the data that they're giving us. Here's the reaction. We have this reactant, and basically it's undergoing a decomposition reaction into 2COCl2 gas. And they're giving us times and total pressure, and this is going to be important to keep in mind. So with regard to the time, they're saying, okay, at time 0, we have a total pressure of 15.76 millimeters of mercury. At 181, it goes up to 18.88. And at 513, it goes to 2279, and 1146 to 2708. Now, these are the total pressures. So we're asked, based on the data, is this a first or second order with respect to the concentration of ClCO2, CCl3? Now, I mentioned that this is total pressure. So one of the ways we have to do this, or the only way we can do this, is we need to figure out which graph is it going to fit best. So if you remember the first order graph versus second order graph, so in first order, I'll write it up here. So in first order, we're looking at we're looking at the natural log of the concentration of substance A versus time. And then for second order, we need to look at the 1 over the concentration of substance A versus time. So 1 over the concentration of A versus time. So we need to find the concentration of A, or in this case, the pressure of A over time. And so that brings me to the fact that we're dealing with total pressure. Notice that the reactant and the product are both gases. And if we're looking at the total pressure, well, it's the pressure of both gases together in the same container. Well, in order to figure this out with regard to the order, we need only the pressure due to the reactant. We don't want the pressure due to the product. So how do we get that? Well, the key is to look at what the changes are in product and reactant. So if I rewrite the reaction down here, so we have ClCO2, CCl3 gas goes to 2COCl2 gas. We can kind of set up a sort of ice table in a way, but we got to look at the change in the two things, right? So we start with a certain amount here, right? And we're going to end up with a certain amount here. So over change. So look at the mole ratio here. So we have, for every one of these, we produce 2 of those. So if you lose a certain amount here, we're going to gain twice as much here. So if we do this in terms of x, so if I lose an x amount here, then I'm going to gain 2x here. Okay, are you with me so far? So I lose an x amount here, but I gain 2x here. Now, if I add these together, what's the overall effect on the overall amount or pressure that I have? Well, if I add these together, so negative x plus 2x, that's going to give me a total of plus x. So overall, for my total, I gain a plus x amount. So if we think of this in terms of pressure, I lose an x amount of pressure from my reactant. I gain 2x amount of pressure for my product. And so the overall change in the total pressure is going to be a plus x amount. Okay? Well, how do I find that plus x amount? Well, let's go to the data, right? So at time 0, I started with a total pressure of 15.76 millimeters of mercury. Well, at the very beginning of the reaction, all I have in my reaction vessel is reactant. So I have 0 product. So this pressure here is due only to the reactant I started with. Okay? So whatever I lose from this amount in my reactant, as far as pressure is concerned, is going to be equal to the amount that I gained in the total pressure. So we got to understand this. So this here represents the overall gain that to my total pressure due to the reaction, right? Because of these. So I lose an X amount from my reactant. I gain 2X amount from my product. So the two total together, I add those two together, I get an X amount gained. So look at the data here. So I start with 15.76 millimeters of mercury. This is only product. Okay, after a certain amount of time, like at 181 seconds, I lost some amount. I lost an X amount from my reactant, but I gained 2X amount for my product. And so the total together means I gained an X amount in my total pressure. Well, what was that? Well, I find the difference between my original amount, which was only the reactant. And so now here, notice I gained some in the total pressure. Well, what was that gain? That's the X amount. How do I find that gain? I subtract. So 18.88 minus 15.76. And when I subtract that, I get 3.12. And that's millimeters of mercury. That's the amount that I gained. But look here. The amount that I gained in the total pressure is equal to the amount that I lost in the original pressure of my reactant. So now I go back to the 15.76. So 15.76, and I subtract the 3.12 from that. So because that's the amount I lost. And that's going to give me, let's see, 3.12. And so when I subtract that, I get 12.64 millimeters of mercury. And this is the amount of pressure that's left over due to my reactant. So I started with this at time 0. Let me put a box around that because that's going to be important. So I start with this as my total pressure with only reactant at the beginning of the reaction when nothing has happened. So, but after 181 seconds, now I've gained this pressure. Well, that pressure, that gain in pressure was a 3.12 gain in the total pressure. And according to this, that gain is the same as the amount I lost in the original pressure, which is the 15.76. And so I subtract that because this is the amount that I lost. So the amount I gain is the amount I lost from the reactant. And so when I subtract that from the original amount I started with, this is now how much I have left in the pressure of my reactant. So I hope that was clear. So now I can see, okay, well, what about after 513? Well, it's the same thing, right? So now I have, this is my total pressure. So I'm going to take that total pressure, 22.79, and I'm going to subtract what I started with, the 15.76. So 15.76, and that's going to give me 7.03 millimeters of mercury. And so now to find out how much reactant I have left at this time, 513 seconds, I'm going to now subtract that from the original amount, 15.76. So 15.76 minus 7.03 millimeters of mercury. Mercury. And that's going to give me, what did I get? 8.73. 8.73 millimeters of mercury. So this is the amount of reactant I have left after 513 seconds. And finally, I can do the same thing at 1164. So the total pressure at 1164, I'll write it over here. So I have 27.08. And again, I'm going to subtract the amount I started with, minus 15.76. And that's going to give me, what did I calculate that? That's 4.44. So that's going to be 4.44 millimeters of mercury. Okay. And now, again, since that's the gain that I got in the total pressure, I'm going to subtract that from the original pressure that I had from the reactant. So 15.76. So 15.76 minus 4.44. Oops, wait, hold on a second. 11, oh, sorry, I wrote down the wrong number. This is 11.32. 11.32 millimeters of mercury. All right, so now I'm going to subtract 11.32, and that I get 4.44 millimeters of mercury left of my reactant. So now I can graph the data to see if I have a first or second order reaction. Why? Because now I have time, and now I have the concentration over time of my reactant for the ClCO2CCl3. So I have the concentration. It starts off at 15.76 millimeters of mercury, and then it goes down to 12.64, and then down to 8.73, and then down to 4.44. So now I can go ahead and do this. But now I have to calculate the natural log of A and the 1 over the A. So I'm going to have to take these values. Concentration and pressure works the same. So I'm going to have to take the pressures here, and I'm going to have to do the natural logs of those as well as the 1 over the pressure. Okay, so let's do that next. Okay, so now I have my table a little bit more organized here. So here are the values I have. So let's do first order. So I know that first order is going to be natural log of the concentration of A, or the pressure of A in this case. And A in this case is this substance here. And so I'm going to have to plot the natural log of A versus time, but I need the natural log of A. So I'm going to take these values here and do the natural log. So at time 0, this is the pressure of my substance. And so in this case, the natural log of A is going to be equal to the natural log of 15.76, which is equal to 2.76. And then for this one, I do the same thing. I have the natural log of A, which is in this case the natural log of 12.64. And that's equal to, what did I calculate? 2.54. 2.54. And then for this one here, at time 5:13, the natural log of A is equal to the natural log of 8.73. And when you calculate that, you get 2.17. And then you take the natural log of A for 4.44. This is at time 11.64. I get natural log of 4.44, and that's equal to 1.49. 1.49. Okay, so now I have the natural logs of A for the times of A. So now I can plot on an Excel spreadsheet. I can plot this versus time, and I can see if the data, if the trend line is straight through the data. Does the data fit a straight line? Okay, but I do the same thing also with regard to second order, right? So in this case, I would have to find the 1 over A. So in this case, for second order, so here's the first order data. And then for the second order, if we kind of reproduce the table here, just to kind of make it clear. So 181, 513, 1164. Now, what we want to do now is find the 1 over A for each of these times. So we're going to take this and we're going to do 1 over A. So that's going to be equal to 1 over 15.76. And that's going to be equal to 0.0635. 0.0635. And then at time 181, we do the 12.64. So in this case, it's going to be 1 over A. And that's going to be equal to 1 over 12.64. That one there. And then when you solve that, you get 0.0791. 0.0791. At 513, we have 8.73. So 1 over A is going to be equal to 1 over 8.73. And that's going to be equal to 0.115. And finally, at 1164, we're going to have 1 over A, and that's going to be equal to 1 over 4.44. And that's going to be equal to 0.225. 0.225. And so now I have the 1 over the concentration or pressure of my reactant versus time. And so now I can plot this data here. I can plot this data with the time and see if I get a straight trend line through the data. Does the data points fit a straight trend line? And so you would do this on an Excel spreadsheet. So I would plot time versus 1 over the concentration, and I would plot time versus the natural log and see which one. And again, just to be clear, this is first order. So here, I'll write it over here. So here, we're talking first order. I'll just write it over here. So over here, this data here is with respect to first order. And this is the data with respect to second order. Okay, so let me show you what I got when I did this myself. So here is the graph for the first order, the ln of A, the natural log of A versus time. So if I show you the graph, so what do you notice? So here you got on the side here, this is your natural log of A. So this represents the natural log of A, and this represents the time. And so look at the data points here. So what we're looking for is a straight line, or the data points. So we have our data points that we plotted. So there's the data points, 4 data points. And the trend line, you'll notice, goes pretty much through the points. We have a straight line through the points, and that's what we're looking for to indicate what the order is. And so this data that we plotted is the data for a first order reaction. And so since we get a straight line through the data points, that indicates that it's a first order reaction. Now, just to be complete, you would do the other one. And so here's the other, So here's the other plot. This is the plot, and you can see here, this is the plot with respect to the 1 over A, right there. So we're plotting 1 over the concentration of our substance versus time over here, time in seconds. And so what you notice right away is look at the data. Look at the data points and the trend line, right? So here you've got the data points, but look at the trend line. The trend line doesn't go through the data point. The data points are not really going, the trend line isn't really going through all the data points. So this indicates that this is not second order. So that is how you would figure this problem out. So that's it for the video. I hope you enjoyed the video. I hope this was helpful, and I hope that this clarified issues with this problem, and I hope this helps you with other very similar problems. So if you enjoyed the video, if you learned anything from this video, then please, by all means, like the video, share the video, hit that like button. Also, do me a favor, subscribe to my channel, help me out. Also, hit that notification bell up there. When you do, click all so you'll be notified by all the videos I put out. And finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you if you have a problem or an issue that you need help with, or if you have a topic you would like me to cover, I would be more than happy to do that for you. Thanks for joining me, and have a great day.